This is an AQA Chemistry video, and it's all to do with the required practicals. I'm going to be taking you through the content, and then we'll be looking closely at past paper questions. In this required practical, we're being asked to make a soluble salt. So that's a salt which dissolves in water. And in terms of the reactants you'll need both an acid and an insoluble metal oxide or metal carbonate. In the example I'm going to show you, we're making soluble copper sulfate. Think about the acid we'll need. That will be dictated by the sulfate, so we'll use sulfuric acid. And my insoluble reactant will be my copper oxide. Just so you know, if you're asked to make a salt which contains a nitrate, you'll need nitric acid. If you need to make a chloride, you'll need hydrochloric acid. And as we know in this example, to make a sulfate, we'll be using sulfuric acid. So always bear in mind the appropriate reactant. But what about our method for making this salt? You'll get a mark for mentioning the correct reactants. Make sure you include any suitable apparatus. So I'm going to say, for this example, add sulfuric acid and copper oxide to a beaker and stir. We want our insoluble reactant to be in excess, so continue adding copper oxide until it's in excess, and you'll see no more fizzing occurring, no more effervescence. We need to remove any unreacted copper oxide, so we're going to filter the mixture using a funnel and filter paper to remove excess copper oxide. Now our next step is to evaporate some of the water, so we're going to heat the mixture using a Bunsen burner and evaporating basin until the crystallization point has been reached. And then our last step is to allow our salts to dry. So leave to dry, and do specify how you're doing this on filter paper. So zooming out, here's my detailed method as to how I'm making copper 2 sulfate from sulfuric acid and insoluble copper oxide. I just want to show you the apparatus. So we've already reacted our copper oxide together with our sulfuric acid. We've made sure the copper oxide is in excess, so then we're using the filter paper and the funnel to remove any unreacted copper oxide, leaving us with a saturated copper 2 sulfate solution, which we've placed in an evaporating basin. This gets put on top of a wire gauze on top of a tripod, which has a Bunsen burner underneath. We're going to use that Bunsen burner to heat our solution in order to evaporate some of the water to reach that crystallization point. And then our last step is to leave those crystals to dry. This question is about making a soluble salt. Plan a method to make pure, dry samples of zinc chloride from zinc carbonate and a dilute acid. If we actually look at the equation, we're using zinc carbonate, we need an acid, and we're making zinc chloride. So what acid must it be? If it's a chloride, it must be hydrochloric acid. So there's our equation. So how do we make a soluble salt from an insoluble reactant and an acid? First of all, we want to add zinc carbonate and hydrochloric acid to a beaker. Do mention all the appropriate apparatus and stir. Remember, we need the insoluble reactant in excess, and no more fizzing occurs, no more carbon dioxide is released. That will also show that we have an excess. Now we need to filter using a funnel and filter paper. Why do we do that? To remove any unreacted zinc carbonate. So now we have a saturated solution. So we need to heat the solution in order to evaporate some of the water. Leave the solution to crystallize and dry. Make sure you specify something like filter paper, drying oven, a warm place. Name 2 other substances that can be reacted with a dilute acid to make zinc chloride. So we know the acid is HCl. Do not refer to zinc carbonate. Your other options are just simply zinc, the metal on its own, as well as zinc oxide. Right, electrolysis. Just to remind you, it means splitting a substance using electricity. And because we're doing chemistry, what is the type of substance? It's going to be a giant ionic structure because we need our substance to be made up of ions. I'm sure you're aware of this, but when you look at an electrolysis chamber, you'll have a positive ion and a negative ion. And your positive ion is your cation, your negative ion is your anion. So here's a really standard electrolysis apparatus. We have the electrolysis chamber, which contains our electrolyte solution. So that's our solution of ions, our positive and negative ions. As I've already said, the positive ions are cations, the negative ions are anions. You'll have 2 electrodes. Now those electrodes tend to be made out of something like platinum or graphite. And why do we use platinum or graphite? Because we need something which is both unreactive and something which conducts electricity. So the electrodes have special names. The positive electrode is known as the anode. And that's going to attract the oppositely charged ion. So it's going to attract negatively charged anions. The negative electrode, the cathode, will attract positive cations. If we were to look at the electrolysis of molten lead bromide, and remember we need our substances to be molten or in aqueous solution so that the ions are free to move. Let's consider what ions we have. We have Pb2 plus and Br minus. So at the anode, so the positive electrode, because opposites attract, you're going to have that bromide being attracted. It forms diatomic bromine, so that's why you need to write Br2. Let's balance that. And then in terms of electrons, in order to balance that, this is our completed half equation. And because electrons are being taken away, we call that oxidation. What about at the cathode? So that's the negative electrode. The Pb2 plus will be attracted, forming Pb, so just lead. We'll need to add 2 electrons in order to do that. So reduction has occurred. Remember the mnemonic oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And don't forget to state observations. With your bromine, you're going to see a brown-orange liquid. With your lead being formed, you'll see a silver-coloured metal. Remember, if you have aqueous solutions, such as aqueous sodium chloride, the fact it's aqueous adds additional ions. It adds H plus and hydroxide ions, as well as the sodium and chloride ions. Do you remember that it's the least reactive element which forms at the cathode? So here's your half equation at the cathode. And then the halogen will discharge preferentially at the anode. So this is what's going to happen at the anode. This question is about electrolysis. Molten sodium chloride is electrolyzed in an industrial process to produce sodium. Figure 8 shows a simplified version of the electrolysis cell used. So let's have a look what we've got. We've got our molten sodium chloride, which means we have Na plus and Cl minus ions. So remember that at the positive electrode, the anode, you're going to have chloride ions being attracted. So there's the half equation occurring there. And then at the negative cathode, your sodium ions will be attracted. So we can see reduction occurring, which is the correct half equation for the production of sodium. I've actually already done that. We need a neutral sodium being produced. It's this reaction here, which is reduction, because electrons have been gained. If you're not sure about electrolysis, because after all it is a difficult topic, do check out my other videos where I go through this step by step. A mesh is used to keep the products of electrolysis apart. Suggest one reason why the products of the electrolysis must be kept apart. Simply because you don't want the products to react to reform the sodium chloride. Which type of particle passes through the mesh in the electrolysis of molten sodium chloride? I talked about these already. We've got ions. Aqueous sodium chloride solution is electrolyzed in a different industrial process. Two gases and an alkaline solution are produced. So what sets aqueous sodium chloride solution apart from before is, as well as the sodium ions and the chloride ions, we also have H+ ions and OH- ions present. So which two ions are present in the aqueous sodium chloride solution in addition to sodium and chloride ions? Indeed, it is the H+ ions and the hydroxide ions. Name the alkaline solution produced. So when you have multiple ions present, when you consider the positive ion, it will actually be the least reactive element which discharges, which means it's hydrogen, leaving sodium ions over in solution. If you look at the negative ions, the halogen discharges preferentially, so the halide ion. So that's the chloride ion, leaving the hydroxide ion over. So what is the alkaline solution produced? It is sodium hydroxide. Explain how the alkaline solution is produced. You should refer to the process at the electrode. So I'm just going to write exactly what I've just been talking about. We're going to say that sodium ions and hydroxide ions are left in solution. Hydrogen ions are discharged at the negative electrode, which remember is the cathode. Let's write that half equation. So our hydrogen ions form H2 gas, and that's reduction because electrons have been added. Let's write what happens now at the anode. The chloride ions are discharged at the anode, so at the positive electrode. There's the half equation occurring there. Because electrons have been lost, we call that oxidation. Now we'll look at all the reactions to do with temperature changes, and that involves endothermic and exothermic reactions. Remember, endothermic reactions take in heat energy from the surroundings, and so as a result, the surroundings get cooler. So you'll see the temperature decrease when you measure that with a thermometer in an endothermic reaction. Exothermic reactions release heat energy to the surroundings, so the surroundings get hotter, and so with our thermometer we'll find that the temperature has increased with an exothermic reaction. It's very important that you're aware of that. Let's look at these energy level diagrams. So with our exothermic reaction, remember that delta H, our energy change, is negative, and what that means is that our products have less energy compared with our reactants, so do make sure that these reactant lines are higher compared with the products. The difference between those two lines is your energy change. Your activation energy, remember, is the minimum amount of energy required for a reaction to take place. With an endothermic reaction, delta H is positive, and as a result, your products have more energy than your reactants, so the product line is higher than that of the reactants. Again, you can find the energy change, and do make sure you can label that activation energy again. In terms of examples of endothermic reactions, we've got cold packs used for sports injuries. Exothermic examples include hand warmers and self-heating cans. Now, the way in which we can investigate the endothermic and exothermic reactions include the following. So we could add a salt to water, such as sodium chloride, the salt, we add it to water. Neutralization reactions, an acid reacting with an alkali. An exothermic reaction, the temperature will increase. Displacement reactions, so when a more reactive metal displaces a less reactive metal. And combustion reactions, which is all to do with burning fuels like the alkane methane. This is a really typical setup. So here we're adding sodium chloride to water. We've got a polystyrene cup which is acting as a good insulator, and that's going to prevent heat loss to the surroundings. We might choose to add a lid again to further reduce heat loss. When we add the two substances together, we'll want to stir to ensure that they're fully mixed so that a maximum temperature can occur. But the best thing to do here is to look at past paper questions. This question is about temperature changes. A student investigated the change in temperature of a solution when different masses of ammonium nitrate were dissolved in water. This is the method used. Measure 200 centimeters cubed of water into a polystyrene cup. Measure the temperature of the water. Add 4 grams of ammonium nitrate. Stir the solution until all the ammonium nitrate has dissolved. Measure the lowest temperature reached by the solution. Repeat steps 1 to 5. Okay, because the temperature's gone down, I'm just going to make a note there. It's obviously an endothermic reaction. It's taken in heat energy. Give the independent variable and the dependent variable. You must learn your variables. Your independent variable is what you change, and your dependent variable is what you measure. So check the methodology. We're using different masses of ammonium nitrate, so that's our independent variable. And then what's our dependent variable? What are we measuring? The lowest temperature reached. Table 2 shows the results. Plot the data from Table 2 on Figure 2 and draw a line of best fit. Let's take the data. Let's draw a line of best fit. Determine the initial temperature of the water. You should extend your line of best fit on Figure 2. Follow the instructions. It's telling us to extend our line of best fit, so that's what I'm going to do here. So we're looking at this temperature right here. We can see that we start at 18.8. Obviously it will vary depending on your line of best fit. How do the results show that dissolving ammonium nitrate in water is endothermic? Already accidentally answered that because the temperature decreased. They talk about the lowest temperature reached. The student repeated the experiment 3 more times. Table 3 shows the results for 8 grams of ammonium nitrate. The student recorded the mean lowest temperature of the solution for 8 grams of the ammonium nitrate as this. Explain why the student included a plus or minus 0.3 degrees Celsius after the mean lowest temperature. So if you were to look at the data here, you can see that the range, we take the highest value, which is 16.8, take away the lowest value, 16.2, to get 0.6. And then the uncertainty is plus or minus half of the range, so half of 0.6 is 0.3. And so we'll show how that works. We're going to take our mean value, 16.5, and then we'll add 0.3 to get that highest value reached, which was 16.8 degrees Celsius. Now we'll take away 0.3 to get 16.2, which was the lowest temperature. What type of error is shown by the results in Table 3? This is called a random error.